When we talk about vector mathematics and electricity and magnetism, normally we're going to be adding vectors, subtracting vectors, and multiplying vectors. So I want to review those operations with you. And I just noticed there's a typo on here. That has nothing to do with this slide. So given any two vector quantities, we can easily add or subtract them. It's a little more complicated to multiply and divide them, and we also have to be more careful about what we mean when we say vector addition, or sorry, vector multiplication. So I'm going to divide that into two parts. And first we're going to start with basic vector addition, and then we'll move into simple vector multiplication. So starting with vector addition. So if we've got two vectors, to add them or to subtract them, we just add or subtract the corresponding components for each of the directions in the coordinate system. So if I have a vector A, and it's got an x component, a y component, and a z component, and I have a second vector B, and it similarly has an x, y, and z component, the sum of those two vectors is if I just add the x components together, and then I multiply that by a hat x, and then I sum the y magnitudes together, and I multiply that by a hat y, and then I sum the magnitudes in the z direction together, and I multiply that by a hat z. Similarly, I can just subtract them by a really similar process, subtracting the corresponding components for each of the directions in the coordinate system. So a minus b is just going to be ax minus bx, a hat x, plus ay minus by times a hat y, plus az minus bz times a hat z. So often this is taught using vector notation, as I'm showing here. What we do is typically we will use what's called the toe-to-tip or heel-to-tip method, where you take the vector and you draw one vector this direction, and then you take the end of the second vector and you put it at the end of the first vector, and the resultant vector a plus b is those two added together. So if this is the method that you're used to doing vector notation, this isn't really going to work for you in electromagnetics. I like to point it out. Some people think they understand vector notation. This is what's going to serve you over here in this class. This might help you visualize it, but when we actually implement it, you're going to have to use this. One important thing to note is that for me to be able to add two vectors, they have to be of the same dimensions. So I was able to add these two vectors because they're both 3 by 1, meaning there's an x, y, and z component. Vectors could have multiple components though, right? It could have could be 3, 5, 2, 1, 7, 9. A vector just has magnitude and directions, and that doesn't necessarily have to correspond with free space. So in this class, it's okay. All of our vectors are going to be 3 by 1 vectors, and so that won't be a problem. But if you're taking other math classes like linear math, where you have to do vector multiplication or vector addition, realize that to add two vectors, they have to be of the same dimension. Also, you can't add a scalar number to a vector. It doesn't make sense to say something like 2 plus a hat x. That's just nonsensical. You can't add a scalar to a vector. It's just impossible. It's a meaningless operation. So adding a scalar in a vector doesn't mean anything. That's not allowed. You can, however, multiply a vector by a scalar. So when we consider how to multiply vectors, the math isn't as easy for addition, and in fact there's going to be 3 different ways to perform vector multiplication. But the easiest is what we're just alluding to, which is scalar multiplication, the multiplication of a single vector quantity by a single scalar quantity. So let me demonstrate this by taking an example. Let's say we have a vector b, and the vector b is equal to 2 units in the x direction plus 1 unit in the y direction. That implies that it's also 0 units in the z direction. And so I'll write this as 2, 1, 0. And if I were to draw that, I would say that it points 1 unit in the y direction and 2 units in the z direction. So this is b vector. So now let's multiply the b vector by a scalar quantity. And by scalar, we just mean something that's got a magnitude. So 3 would be a perfectly allowable scalar. 3 times b is just going to be 3 times 2 a hat x plus a hat y. And so that's 6a hat x plus 3a hat y. So if I were to plot that, 1, 2, 3, 4, 5, 6 in the x direction, 1, 2, 3 in the y direction, that is the resulting vector 3b. And from this plot, we see that the scalar multiplication operation changed the magnitude of the vector. It made it longer, but it did not change the direction. This angle theta is the same as that angle right there. So scalar multiplication does not change direction. It only changes magnitude. There's another type of scalar other than a positive scalar, and that's a negative scalar, right? Real numbers go both above 0 and below 0, and so I can do something like minus 1 times b. And so that is equal to minus 1 times 2, 1, 0, which results in minus 2, minus 1, 0. X component, Y component, Z component. So if I were to plot that in the X and the Y plane, I have to go minus 2 in the X direction and minus 1 in the Y direction. So that's the point right there. And from that, what you see is that multiplying a vector by a negative number rotates the vector by 180 degrees. So it did change the angle. So sometimes scalar multiplication can change the angle in the case that the scalar multiple is a negative. It did not, however, in this case, change the magnitude. Now, if I had multiplied by like minus 2 b hat, that would change both direction and magnitude. But so those are kind of the simplest vector mathematics that we can do. Vector addition, where we add two vectors, and then scalar multiplication of a vector, where we take a scalar number and multiply it by a vector quantity.